It's the simple transmission line consisting of two conductors. There is a direct conductor and the back conductor. The length of the line is supposed to be infinite. This means that we ignore side effects that occur at the beginning and the ending of the transmission line. Again, this case has a simple analytical solution. You can see the equation on the screen. This formula gives accurate results if the wire is thin comparing to the distance between wires. Let's simulate this case in QuickField. I have the problem ready. The problem type is magnetostatics. The model class is plane parallel. And I will calculate the inductance value per 1 meter of depth. This is my model. This is the air. This is the back current. I set -1 ampere in this conductor. And this is the conductor with direct current, 1 ampere. And this is the faraway boundary. With zero magnetic potential. Let's take a look at the simulation result. You can see the field lines. I will switch on the vector plot. Now I can see how the flux flows, and I can measure the flux to calculate the inductance. I will build the contour between conductors to calculate the flux. The magnetic flux is 1.921 microwebers. And if I divide this value by the current value, which is 1 ampere, I will get the inductance of 1.921 microhenries. Let's compare this value with the theoretical result. You can see in QuickField I get the smaller value than the theoretically calculated. There is a difference but what have we missed? We forgot about self-inductance of the conductors. Let me show you. There is a flux inside the conductor. And my contour, my integration contour, does not include this flux. It is not calculated here, so we get smaller value. Let's correct my mistake. I will correct the contour and add small parts to my contour to calculate both external and internal flux. Now, what is the flux value? The flux value is 2.12 microwebers, and the inductance will be 2.12 microhenry. Again, let's compare with the theoretical result. Now I get the bigger value than theoretical calculated. Why is it happening again? Let's take a look at the conductor. Please take a look at the field lines in conductor. Only center part of the conductor, only center current, is linked with the full flux. It is linked with internal flux and external flux. The current that flows on the surface of the conductor is not linked with internal flux. It is linked with external flux only. To get accurate value of inner inductance, we should take into account the amount of the current that is linked with the inner flux. In fact, this function is already implemented in QuickField. It is called the flux linkage per one-term integral. The value I get is 1.01 microwebers. Now we should remember that there is the second conductor, and the total flux would be 2.02 microwebers, and the inductance will be 2.02 microhenry. Let's compare with the theory. 2.02, 2.03. Now the difference is only in the third digit, and it is less than 1%. And what about the built-in inductance wizards? You can use them as well. Let me show you how to use the wizard in this problem. The wizard asks to specify the direct and back current to calculate the flux. Then you should specify the current. And this is the inductance value. 2.2. Very close to the theoretical result. The inductance wizard has the second approach based on the magnetic field energy calculation. Let's try to calculate the inductance through the magnetic field energy. I press the button to calculate the magnetic field energy, and QuickField, then I choose the current, and QuickField gives me the inductance value. In fact, you can calculate the stored energy manually. You need to select the entire region, and use this integral magnetic field energy. 1.0124 1.0124. There is no magic here. You can use either way manual calculations or built-in wizards to find the inductance value. Now let's move to the next example.